as the last part of our simple harmonic motion little introduction, what happens if it's not a mass on a spring? What happens if it's some other system? Like, for example, the simple pendulum, or actually, let's just call it the pendulum to start with. So what is a pendulum? The pendulum is a point mass on a massless string, to be really specific as to what it is, all right? And so what we want to do is prove, is this thing in simple harmonic motion? I think we, if you remember way back to the beginning of the first video, we actually showed it's not, and for reasons we'll go through in just a moment. So we're going to go through two ways of doing this, one which I think is a little bit harder than the other, and we'll see why. So first, there's my mass, or there's my pivot point, and then we'll draw a mass on the end of a string. I'm going to draw its path through. I think conservation of energy will show that as long as the mass is not encountering any non-conservative force, that it's going to get up just as high as there. So how are we going to do this? The way that we're going to do this is by doing a free body diagram. So I've got my FG here, and I've got my T here. So here's the differentiation in methodology. The first methodology would say sum of forces is the way to go on this, because that's the way we did it in the other way. I'm going to actually posit that sum of torques is a better thing to use here, because with the sum of torques, I mean, the object is moving in a circular path, and so that always just makes me think that torques is the right way to go. So I'm going to actually show it both ways. I just think the torques methodology is a lot simpler. So let's do this sum of torques. The first thing we have to do is establish some directionality. So if we say that counterclockwise is positive, right? The next thing we need to do is establish a position function. Because remember, every simple harmonic motion is a d squared some position function with respect to t squared is equal to negative omega squared that same position function. Well, here, if I'm doing this with torques and the object is going around in a or is on a circular path, the logical position vector to use is theta, right? So I'm going to define theta is equal to 0 at the place where the object would be and at stable equilibrium, because that's the requirement of this function, right? So if that's theta, I need to make theta is equal to 0 at the stable equilibrium point. Here's my theta is equal to 0. Now, I already stupidly made counterclockwise positive because I wanted this torque to be positive. So that means that the initial position of this object is actually negative theta. So that's going to come into play. So here we go about that. So if I do sum of torques about this position here, or about that, is equal to I about that position alpha. Let's see what I get. So I have a positive torque due to gravity is equal to I. Well, it's a point mass, which is mr squared. We call r the length of the pendulum here L, so that's ml squared alpha. And I'm going to turn alpha into d squared theta dt squared, because I'm trying to get it to look like this to prove it's in simple harmonic motion. Great, so next step down, plus, so this is the force of gravity, mg, and then, oh, I need the lever arm distance. Well, here the lever arm distance has got to be this distance here, which is constantly changing over time, which is good because I know in a simple harmonic motion, the restoring force, or in this case, the restoring torque, has to change over time and has to decrease as I go closer to the equilibrium position, which this does. So what is that distance there? Looking at that, that is L sine of, in this case though, negative theta, right? Because that's that position. Got to work that position in. So what do I have here? L sine negative theta is equal to ml squared d squared theta dt squared. So now let's do a bunch of canceling. The m is going to go away, which is nice. One of the L's goes away, which is nice. Let me move that L over to the other side. So I've got d squared theta dt squared is equal to g over L sine of negative theta. Okay, that's what I've got when I clean it up. Well, it's getting closer to looking like this, but there's a couple of problems. What problems do you see? Well, the first problem you should see is that there's no negative sign here, and there needs to be. The second problem you should see is this is sine of some theta, not theta itself. Damn it. The pendulum will not go into a simple harmonic motion. It goes into a harmonic motion. So that's a distinction that we have. So, damn it. Oh, how about we define something that's called a simple pendulum that is different than a pendulum? Well, you know, Vaughn, can you just do that? And I'm going to say, yeah, I can, because I'm going to exploit something we talked about a long time ago. What happens if I take the limit? Well, actually, first off, let's deal with the first problem. Sine of negative theta? That's negative sine of theta. So I get the negative sign the way I want it. So that got rid of one problem. Now, let's actually look at what we would have done if we had the opposite declaration. So if I would have had clockwise positive, then this would have been a positive theta. Oh, but that would have been a negative torque then at that point. So either way, I end up with that negative sign. Or even on this, when I'm over here and theta is positive, that torque is negative. Awesome. I get that result no matter what I do. So that negative sign popped out the way I needed to. Awesome. No problems there. So what we're going to do here, now I'm going to do this parentheses, is I'm going to say, what happens if we make it an agreement? And our agreement is that we agree to keep theta really small. So hopefully you remember when we did the Maclaurin series expansion, what was true about the Maclaurin series expansion of sine. So sine of theta, we did it with sine of x, but actually I'll show sine of x. We prove with the Maclaurin series expansion that that was equal to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth plus dot, 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 dot. And we showed that as long as we agreed that x had small values, that we could ignore the rest of the terms. So we're going to do the same thing here. And we showed that what did it mean to be small? Well, as long as theta was under about like 15 degrees, we showed that you were within 1% of value. And there was a rough equivalence between sine of x and x. Because once I take that, then I can just go negative g over L theta, put the negative sign there, is equal to d squared theta dt squared, right? This is something that's called the small angle approximation, as we called it. And so what we're agreeing now is that the simple pendulum is a pendulum where we restrict the motion within certain bounds. So what we have here is not necessarily true, folks, but it is functionally true for theta for small values. And so if I don't really care all that much about true precision on this, because even if theta is like 20, the approximation is not that far off. We're just introducing a 2% error instead of a 1% error. And if we're willing to keep theta within 10%, we're introducing less than 1% error. So it's all about like, what do I need this equation to do? This is good enough for most things, so we're good with it. So if I look at this then, for the simple pendulum, that must mean omega squared is equal to g over L, right? So omega is equal to radical g over L. Hold on, that's starting to look familiar. Remember that omega is equal to, actually I'm gonna move this over here so I have more space. Omega is equal to radical g over L. Omega was equal to 2 pi over the period, radical g over L. Oh no. No, look at that. Period is equal to 2 pi radical L over g. That's the equation for the simple period pendulum we learned last year. But now we've derived it. Isn't that so neat? I think that's neat. So the idea here is that I can use sum of forces or sum of torques in order to derive what I'm trying to do here is create something that looks like the characteristic equation for simple harmonic motion, then whatever's in front of the position function is my omega squared. And once I know omega squared, I can find out what the period is. So there you go. So let's do another example of that just so you can see it. And like I said, I could do this with sum of forces, but rather than having I alpha, I have MA, right? But here I would have sum of forces. What force would I use? I would just use the tangential component, which would be the mg sine of theta. So you can see kind of the same sort of ideas would pop out there, but we're not going to go into that because that solution is just a little bit too annoying. So there you go. So what's another system? Oh, one of my favorites. It is the swinging bar, because the swinging bar can also be like a pendulum. So when I don't have just a mass on the end of a string, I have what's called a physical pendulum. It doesn't even have to be a swinging bar. I can take, I don't know, I have a sphere on the end of a stick, and I could pivot that and then tilt that to the side, and that would go into a harmonic motion, if not a simple harmonic motion, right? So physical pendulum, weird stuff hanging that you displace to the side and let it go into, I don't know, some sort of motion. So we're just gonna do a bar. So here's my bar, and I displace my bar to the side, right? Same sort of analysis here, folks. We'll just keep clockwise positive, and there's my theta. So what I need to do is I still need to do forces. So I'm going to do here, that's where the center of mass of that object is. Boom. And so here, I'm assuming that that's halfway down because if it's a uniform bar, but I don't have to. Let's just call D the distance to the center of mass of the system that's hanging down, because that's going to mean that if this is a negative theta, that my lever arm distance is going to be L sine, or excuse me, not L, but D sine negative theta, which is going to be helpful for our analysis. So there we go. So if I do sum of torque about that point, whatever that point is, I about that point, alpha. So here we go. So that's going to be, as we decided, a positive torque due to gravity. I'm just going to leave it I about that point, whatever it is, alpha. So that's going to be the mass of the system that's in that motion times g times d sine of negative theta is equal to I. And then we'll turn this into d squared theta dt squared. Let's clean that up then. So I've got negative mgd, right, sine of theta is equal to, actually I want to move the I over to this side about that pivot point, d squared theta dt squared. It almost looks right because I've got d squared theta dt squared. I've got the negative sign. I've got a constant. Now all I need is, this can't be sine of theta, it has to be theta. I'm going to take the limit as theta approaches 0. So the physical pendulum still has to abide by the small angle approximation. Negative mgd over I about that point. Theta is equal to d squared theta dt squared. So what does that give us then? This all must mean omega squared. Therefore, omega is equal to the square root of mgd. Remember where d is. Where's the center of mass of that system with respect to the pivot over I, and that's just the moment of inertia of the system. And so then I've got the following, that the period of this physical pendulum is 2 pi radical I over mgd. Okay, so there you go. Now, inevitably, just so that we're perfectly aware of this, remember I is going to have stuff like m's in it, so that m down here is going to cancel, right? Because moment of inertia always has mass in it. It's also going to have distance squareds in it. So this is going to end, no matter what this weird system is, as 2 pi radical some distance over g, right? That's the way that that's going to come out. So what do we have there? Just to wrap, by the way, that is a beautiful equation. I'm going to show you an example of it in a second. I had a couple of things. I had the simple harmonic oscillator, which had the period was equal to 2 pi radical k over m. I had the simple pendulum. Period is equal to 2 pi radical L over G, And then we had the physical pendulum, and that's period is equal to 2 pi radical I over mgd. But we said that that's going to just boil down to some sort of distance over g. Look at those equations. There's a lot of similarities. One, got the 2 pi, talking about that cyclical motion. Got the radical, right? Oh, actually, sorry, this is m over k. Oops, right? Notice, what's in the bottom of each of these? K, G, G. Oh my God, for the simple harmonic oscillator, K is what's trying to bring it back to, the spring is what's trying to bring it back to equilibrium. In the simple pendulum and the physical pendulum, gravity is trying to do that. What's in the numerator every time? M. Oh, M's about inertia. The more inertia, the longer the time. Oh, but this is not about inertia. Inertia is mass, right? Except that moment of inertia, distances matter. Moments of inertia. Every simple harmonic motion, the period is going to be 2 pi radical some inertial term over some restoring force term. This is weird as these things can get. That is the truth at the end of it. That the time it takes for this thing to oscillate back and forth is a function of the inertia of the system and what's trying to bring that thing back to its lowest energy state. Okay, so that being said, I'm going to do one last thing, and then you should have all the information you need for when you go do this in college. I'm going to do this with the simple harmonic oscillator because we know all the results, so it's nice and easy. So let's say that this is the equilibrium position. Here it is. We said that the energy of this system was equal to its kinetic energy at any moment plus its spring potential energy at any moment, right? So here we go. If I want to know the period of this system, there's another thing that I can do here. What I can do here is realize that if I take the derivative of this with respect to time, I get a super interesting result. Because watch, this becomes dE dt is equal to, well, the 1/2 m is a constant. I've got d dt of v squared plus 1/2 is 1/2 and k are constants, d dt of x squared. Now, if we're in simple harmonic motion, what's true about dE dt? You're right, it's equal to 0, right? The energy of the system is not changing over time. That's 1/2 m. Now what I've got here is we know that for this system, v is a function of time. So that's going to be 2v dv dt, right? 2v dv dt. We're just doing chain rule. If you want to see that a little bit more specifically, we can show that as a, v times dv dt plus then v times dv dt, if you think of it as v times v and the derivative of that, so same difference, plus 1/2 k times 2x dx dt, yes? So let's just cancel out some things that are going to cancel. The halves cancel with the 2's. Let's see what else. Let's move one of these things over to the other side. So let's say I've got negative mv dv dt is equal to kx dx dt. All right, well, dx dt, what's that? That's v. Negative mv dv dt is equal to kx v. Oh, the v's go away. Let's move everything around. dv dt is just d squared x dt squared is equal to, negative k over mx. It's simple harmonic motion. Why do I show that the energy analysis comes out to the same thing? I will tell you, in some really complicated systems, doing the force or the torque analysis because of the geometries of the system are really awful. And sometimes it's just so much easier to write a simple energy equation for each of them and just do the derivative work for that, and it comes out to the same thing. So if you're having difficulty with these problems and trying to find because now finding the period simple, because omega squared is k over m, so that means that omega is square root of k over m, meaning the period is 2 pi radical m over k. If you're trying to find the period of a weird system, sometimes writing a generic energy equation, taking the derivative of it with respect to time, getting it into this form. Sometimes you get it close to this form, you have to do small angle approximations. Boom, there you go. That's pretty much chapter 13, everyone. At least giving you a grounding, so if you get to college, you have some resources at your beck and call for watching this if you think this might be helpful in terms of figuring out how to do problems.